Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 7 of Module 2, wherein we are discussing the electrochemistry part. Now friends, in our earlier lectures, we have seen the types of electrodes. We have also seen the cell with electrode concentration and the cell with electrolyte concentration. Now, in electrolyte concentration cells, we have also seen the cells with transference and cells without transference. Now, friends, in this particular lecture, we will go ahead and we will construct our ideas based on whatever we have learned, and we will try to see a few of the numericals based on the ideas we have seen, and then further we will be looking for the applications of electrochemistry or EMF measurements that we have learned so far. So to begin with, let us start with this numerical wherein we need to calculate the EMF of this kind of cell. Now in this cell, the zinc amalgam electrode is in contact with the zinc sulfate solution of 1 molar, and whereas this electrodes of zinc amalgam of two different concentrations are taken, one of 0.1 molar and one of 0.01 molar. So this is clearly an example of electrode concentration cell wherein my EMF can be calculated using this particular formula. Now at left hand side electrode we can see that there is a loss of electron, and at right hand side electrode there is a gain of these two electrons, and therefore definitely the n is equal to 2, and therefore my Nernst equation gives me like EMF of cell will be of this fashion, and using this formula I can calculate the EMF of this cell. Based on the same idea, I can actually calculate the EMF of this cell if the transport number of nitrate ion is given. We have seen the idea earlier also while discussing the this particular type of cell wherein the EMF of the cell is dependent on the transport number. So if this is my particular cell wherein two different concentration cells are cells are taken, and silver electrode are in contact with the silver nitrate solution of different concentrations. So at left hand side electrode, obviously there is a loss of one electron, and at right hand side electrode there will be a gain of electron. Now here n is equal to 2, and therefore the two liquids are in direct contact, and therefore it is the electrolyte concentration cell with transference, and therefore we can have this formula EMF of cell is equal to this, and I can actually calculate based on this formula the EMF of the cell that we have obtained over here. Similarly, we can go ahead with this idea. We can take another example of this type. Herein, see the cell EMF at 25 degrees centigrade is given as minus 0.027 volt, and we need to calculate the transport number of H plus and Cl minus ions. Now, if the cell reaction is given like this, okay, now you can see over here, this is the example of concentration cell with transference because two solutions are in direct contact. Now, in such cases, the cell EMF is given by this particular expression. We know that this ECL is equal to 0.0591 into 1 minus T plus log of C2 upon C1. In our previous lecture, we have seen this formula. Now, we know the concentration of second cell C2, we know the concentration C1. And if I substitute these values, like EMF I have substituted over here, and if I solve this expression little bit, so I get this form, the expression in this form, and if I rearrange the whole formula, I get the transport number of cation in this form. So with this I can get the transport number of H plus ion as 0.85, and then transport number of anion is given by 1 minus T plus. So the transport number of anion is 0.15. So transport number of hydrogen ion is 0.85, and transport number of chloride ion is 0.15. We can calculate over here. We can utilize this formula in n number of examples, and therefore we can solve n number of numericals based on it and practical applications. So now what we'll do, friends, we will proceed further to look at the applications of EMF in this lecture. So friends, basically the application of EMF measurements are varied, and there are n number of applications. Just to name a few, we have listed here. that you can determine the pH of solution. Of course, there are a number of various ways to measure the pH of solution. So we can utilize this idea of EMF measurement for the determination of pH of solution. We can determine the endpoints using potentiometer titration. We can determine pK values of acid and base. We can determine the various thermodynamic functions, Gibbs free energy, enthalpy, entropy using Gibbs Morse equation, and the ideas of delta G is equal to minus NFE. So there are various number of applications. We can determine the solubility product and solubility of sparingly soluble salt. We can determine hydrolysis constant and hydrolysis. We can determine its application in many ways. We can have the application of EMF. Even nowadays, this EMF measurement can be applied in design of sensors. We will see a glimpse of it as well. So let us have a look at all these aspects at one by one. So applications of EMF measurement, one of the major application is determination of pH. Now we know what is pH. It is given by this formula: pH is equal to negative logarithmic of H plus ion concentration. So now there are various methods of pH determination. We can determine the pH using the hydrogen electrode. I can also determine using quinhydron electrode. I can also determine it using the glass electrode. There are other ways as well, but then using individually using these electrode, let us see how pH can be determined with the help of EMF measurements. Now if I take the example of hydrogen electrode, say my hydrogen electrode is represented like this. Okay, now the oxidation reaction is given by, obviously, by this expression, and therefore based on this expression my Nernst equation will be of this fashion, isn't it? Now this is the pressure of hydrogen, and for this particular hydrogen electrode, I know that the standard EMF is 0 for hydrogen electrode. And if I can maintain the pressure of this hydrogen at 1 atmosphere, I can rewrite this particular expression of this form, isn't it? And this particular form can get me of this pattern, that is 2.303 RT upon F into pH. Now if I know the EMF, all these values are known to me, I can find out pH, and therefore this pH can be EMF upon 0.0591 for the standard condition. So this equation shows that the equation oxidation potential of electrode is directly proportional to the pH of solution, and this idea can be utilized in n number of ways. We can even determine the calomel EMF of the calomel that you prepare, calomel electrode you prepared in your lab, and you can prepare a series of solutions of different pH, and from that you can actually calculate the EMF of calomel electrode, and you can find out whether the calomel you have prepared is correct or not, or it is good one or not. So there are n number of application, as I said. So one of the way of determining pH is this as well. Next, we can determine the pH using the quinhydron electrode. Actually, basically what is quinhydron? Quinhydron is equimolar mixture of quinone and hydroquinone. So basically a pinch of this chemical is added to the solution whose pH is to be determined, and a platinum wire is dipped into it. So basically the equilibrium is set up particularly, you can see over here, of this particular fashion. So quinhydron electrode, although very useful, it has got certain limitations. Now this electrode basically gives sometimes the erratic results in presence of ammoniacal ions, because its polarity changes above pH 7.1, and therefore when used in combination with the normal calomel electrode, particularly it cannot be used above pH 8. That's the limitation for this particular case. But then if I would like to utilize it, I can actually write down this particular equilibrium, and I can write down this Nernst equation of this fashion in this case. Now since quinhydron is the equimolar mixture of quinone and hydroquinone, I can write down at equivalence point I have this. So at equivalence point, if I have this, I can find out the EMF of this fashion. So I can substitute the value of pH. So I can find out from this the standard quinhydron electrode potential and EMF of cell. I can find out the pH. So standard quinhydron EMF is given by this 0.6994 volt, and this EQ is the experimentally determined EMF, and therefore using both these values I can find out the pH. Now it should be noted here that this EQ and EQ standard are oxidation potential. So if I use the reduction potential, my formula get reversed, and I can utilize this particular formula for determination of pH of the solution using quinhydron electrode. Now I can determine the pH of solution using glass electrode as well. Basically, the commercial pH meters they make use of glass electrode, or the standard calomel electrode, glass electrode and standard calomel electrode assembly to measure the pH. You must have seen the single electrode many a times that comes along with the standard potentiometer or standard pH meter. Now, this glass electrode is a special type of electrode called as ion selective electrode. It consists of a glass tube and a thin glass bulb, and this particular bulb is filled with zero point 0.1 normal HCl, and a silver or platinum wire is dipped into it, and the bulb is immersed in the experimental solution. Now what is happening when the bulb is immersed into the solution? Due to the difference in concentration on either sides of the glass bulb, some potential develops on the glass membrane, and this potential depends on the concentration of H plus ions in the solution. And since I can find out the H plus ion concentration, I can find out the pH of solution. You can see over here, this particular is a shape of the glass electrode, wherein the zero point 0.1 normal HCl is filled into it, and the platinum or silver wire is dipped into it. So I can utilize this particular expression. I know the standard EMF of it, and I can measure the EMF of this electrode. And then if these are the glass electrode, if these are the oxidation potential of glass electrode, I can find out pH like this. Or if these are the reduction potential, the formula is reversed, and I can find out this particular this way I can find out the pH of solution. So this particular is a representation of my glass electrode when it is dipped into the particular solution. Okay, so this is what all about the determination of pH using different electrode. So I can I can determine the pH using standard hydrogen electrode. I can determine pH using the quinhydron electrode. I can determine pH using the glass electrode. These are the different ways of determining, or these are the different ways of utilizing EMF measurement in the determination of pH. Next, there are n number of applications of EMF measurement in potentiometric titration. I can carry out different potentiometric titrations for different purposes. There are many titrations I can utilize for this purpose. There can be neutralization titration, there can be redox titration, there can be precipitation titration, and using these titrations I can utilize this concept in determining the various parameters. So basically every electrode is reversible with respect to particular ion in a solution. This we know very well. Now the potential of electrode is dependent on the concentration of that ion. So if concentration of that ion changes, there is a subsequent change in the electrode potential. Now, if we can construct a cell which is combining of this electrode with the reference electrode, I can find out the EMF of cell, and this EMF I can see that it will be changing along with the change in concentration. Now the electrode whose EMF changes with the concentration of ion, they are actually called as indicator electrode that we have seen. And rest of the other electrode whose EMF is known, they are called as the reference electrode. So usually, as we all know that generally calomel electrode is used as a reference electrode. So now if the titration in which the equivalence point is detected on the basis of change in electrode, or in which we can find out the electrode potential, or there is a sharp change in the electrode potential, such titrations are called as potentiometric titration. Now in basically the potentiometric titration, a known volume of given solution is usually taken, and the reversible electrode is basically dipped into it. So when I dip into it, it is coupled with the reference electrode, say for example calomel electrode, and then in that case I can record the EMF. So the titrant is added from burette in small installment, and EMF is recorded on the regular basis. And simultaneously, I can find out the change in EMF versus change in volume. So what is the aliquot of volume I am adding, and against that, what is the change in EMF? So with this data, I can plot a graph simultaneously while performing the titration. So a graph is plotted between volume of titrant added and the EMF of cell. So now I will be getting some kind of curve. So the point at which the EMF changes is fastest or the drastic one is actually its equivalence point. You can see over here. So if I get the plot of delta E by delta V, change in EMF against change in volume, and if I get this first derivative plot like this, I can find out there is a drastic change in EMF at this particular point. Okay, so where this change is drastic, it is called as the equivalence point. So if I overlap this graph with this particular graph, EMF against volume of titrant, I can find out where is my endpoint. Okay, so this particular graph and this particular graph, it take or this particular graph, they can give me the maxima or minima, and this maximum peak at which I get a drastic change can lead or can give me the endpoint. So basically, with these potentiometric titration, they can be of neutralization titration type, redox titration type, or precipitation titration type. Now in neutralization titration, what happens? Basically, in such type of titrations, we take the solution which contains H plus ion, and titrant usually contains the OH minus ions. So the concentration of H plus ions goes on decreasing during the titration, and therefore any electrode reversible with respect to H plus ion concentration, say for example, if I take the hydrogen electrode, glass electrode, quin hydrogen electrode, etc., they can be used as an indicator electrode and dipped into the experimental solution. And a calomel electrode is used as a reference electrode. So they can be connected through salt bridge to construct the cell, and the EMF is measured by potentiometer. So the nature of the graph obtained, it can be shown like this particular graphs which are shown over here. It varies from experiment to experiment. Now, similarly, I can study the redox type of titration. We will see one by one the examples of this titration. Now, what happens in redox type of titration? Now, in this type of titration, in redox titration, the oxidation state of some ion changes due to the reaction with titrant. That is very simple. So, in such case, a platinum electrode dipped in the solution, it acts as a redox electrode, and it is coupled with the reference electrode and connected to potentiometer. Now, due to change in ratio of ions of the reacting species, potential changes, and this potential change can be noted down like this graph where it is shown like here, isn't it? Now, say for example, solution containing ferrous and ferric ions. Now, during the titration of ferrous, it get converted into ferric. So I can actually obtain the EMF change as I go on titrating these ferrous ions to ferric ions, isn't it? So oxidation takes place in forward direction. Similarly, I can utilize this concept for carrying out the precipitation titration. Now, in this particular type of titration, particularly in precipitation titration, two ions they combine to form this sparingly soluble salt. Now, what happens near the end point? One of the ion is completely precipitated, and when it is completely precipitated, the EMF changes very rapidly. You can have the example, say most common titrations of these types, they are titrations of halides with silver nitrate. You can see the silver nitrate titration with KCl. So you can see the precipitation of AgCl. We will see one of the example of this type. So the electrode assembly of such type of titrations are silver electrode in contact with the silver nitrate solution, or silver in contact with the silver chloride. But the concentration cell which we form, they are usually of the type silver electrode dipped in silver nitrate solution, isn't it? And at the end point, what happens? All the silver ions, they are consumed and precipitated as silver chloride, and therefore the rapid change in EMF usually takes place in such type of titration. So based on this particular concept, I can find out at what is the complete precipitation state or endpoint of this particular titration. So without using any kind of indicator, I can carry out neutralization titration, I can carry out redox titration, I can carry out precipitation titration. There are n number of other applications as well. Based on that, I can find out the solubility of sparingly soluble salt, I can find out the solubility product, I can find out the hydrolysis and hydrolysis constant as well. So but there are n number of applications, n number of practical experimentation, n number of industrial applications you can utilize of this EMF measurement. Let us see what particularly happens when we see the example of application of EMF in redox kind of titration. Now, this is particularly the example of ferrous ferric and ferric serous system, wherein at left hand side electrode the oxidation is taking place, where ferrous is converting into the ferric solution, and at right hand side electrode the reduction is taking place, where ferric is consuming the electrode and reducing it to serous. So the redox potential value of this ferric to serous system can be determined by potentiometer titration. This is particularly a redox type of titration. We can perform this titration very easily in laboratory. There are two reactions, obviously. One is oxidation at left electrode and reduction at right hand side electrode. So at left electrode, we need to take the case of ferrous to ferric, and therefore at particularly right hand side electrode there will be reduction of ferric to ferrous. So the electrode reaction, they can be shown like this. Now the electrode potential corresponding to this will be of this particular fashion. Say E1 is equal to E1 standard plus RT upon F ln of ferric upon ferrous ion concentration, and for right hand side electrode I can write down like this. At neutral half neutralization point, what will happen, I can write down at half neutralization point this particular expression, that is EMF of cell is equal to E calomel minus E standard of this ferrous ferric conversion. Also I know that at equivalence point both the electrode potential are same, isn't it? So I can write down this E cell is equal to E calomel plus E1 or E2, and using this concept I can find out this EQ is equal to E1 standard plus E2 standard upon 2. So I can take half of it, because it is a half equivalence point. It is at equivalence point they can be equal. Once I know this, I can follow these steps. I can plot the EMF against volume of CAS, ferric ammonium sulfate, and a plot of delta E by delta V against volume of this ferric ammonium sulfate, we obtain the neutralization point. Once I obtain the neutralization point, at half neutralization we can obtain E cell from graph. We will plot a graph of EMF against volume and delta E by delta V against volume. So delta E by delta V give me the sharp peak, and sharp peak when I overlap with the graph of EMF versus volume, I can get the endpoint. So at exactly half of the neutralization point, I can find out the EMF of cell. Now from this value, the EMF of cell and EMF of calomel, that is minus 0.2415 volt, we obtain the standard EMF of this steric serous system. At equivalence point, both of them they are equal. I follow this particular expression. Substituting the values, I can find out the EMF of cell at equivalence point, E2 standard using half neutralization point, and therefore I can find out this E1. So I can you definitely find out the EMF of the system using this particular expression. So this is one of the very simplest possible experiment that I can carry out in laboratory, which usually people do at our laboratory. And this is one of the very interesting application of EMF measurement. We can take many other examples of redox couple, and it can be carried out. Similarly, the another application of this EMF measurement is determination of pK value of acid, weak acid or weak base. So if I titrate a weak acid with a strong base, and if I measure the EMF potentiometrically, then actually at half equivalence point, what happens? At half equivalence point, my this HA will becomes equivalent to this anion concentration. Basically, the dissociation of weak acid is of this pattern. Now, dissociation constant is given by this. Okay, if I take log of both the side of this equation, I get this particular expression. Now I can write down pK is equal to pH plus log of this salt up, particular salt upon this concentration of this anion. Now at half equivalence point, I know that this is going to be equal. So if they are equal, so log of 1 is equal to 0, and therefore at half equivalence point, my pH is equal to pK. So if I know pH, I can find out pK. How to find out pH? pH, for this we have got this formula. Earlier also we have seen that pH is equal to minus of E cell plus EMF of quinhydron minus E standard EMF of standard calomel upon 0.0591. So I know the standard quinhydron electrode potential is 0.6994, and standard calomel EMF of standard calomel electrode is 0.2415 volt. So if I substitute these values, I can find out pH. So at this particular EMF, if I find out this particular pH, this pH is nothing but my pK value. Similarly, I can find out the pK of base as well, isn't it? Apart from that, uh, EMF measurement has got another interesting application of determining the transport number. Now, the basically, how can we find out transport number? So if I know that the current of any solution of electrolyte is actually carried out by virtue of the migration of ion, this we know very well. Now this migration is between the electrode, and it is actually proportional to the speed of that particular ion. So in between two electrodes, these ions, they are traveling. Now, so as the cation and anion, usually they have different velocities under the same potential gradient. That this we know very well. And therefore, the quantity of electricity carried by the cations in one direction will also be different. And therefore, the fraction of the total amount of electricity carried by an ion is known as its transport number. So if say U plus or U minus, if I represent them as the ionic mobility of cation and anion respectively, and then we have this particular expression T plus and T minus, transport number of cation and transport number of anion, as in form of their ionic mobility as this. So the transport number of cation and anion, they can be find out using their ionic mobility. Now my job is to find out these particular numbers using the EMF. Now how can I write down? Say suppose for example, if I take the example of concentration cell of this particular fashion. So silver electrode dipped in the solution of silver nitrate of two different concentrations. So the EMF of this cell with transport number, it can be given by this particular expression. Okay, this we have seen earlier. And in addition, the EMF of cell without transport, if I eliminate the liquid-liquid junction potential, it can be given by this particular expression. Okay, so on solving the equation 64 and 65, we usually get this particular expressions. So I have this transport number of anion in form of this EMF, and then from this particular transport number of anion, I can find out transport number of cation, that is 1 minus transport number of anion. So using the value of E1 and E2, I can calculate this transport number of anion, and from transport number of anion, I can calculate the transport number of cation as well. So this is how I can determine the transport number using the EMF measurements. Similarly, I can utilize the concept of EMF measurement for determination of solubility product. Say I can determine the solubility product of silver chloride. So solubility product is given by KSP is equal to concentration of silver ions plus concentration of chloride ions. Now this is AB type of electrolyte, isn't it? Now the stoichiometry is 10, 1:1. Now EMF is given by this particular expression, and E2 is given by E1 is given by this particular expression, E2 is given by this particular expression. So I can find out the EMF of cell in this pattern. So basically what happens, we have seen in the precipitation titration that the ion concentration at the equivalence point is determined by the solubility product of the sparingly soluble salt, which is usually formed during the titration. Now, in this particular type of titration, what happens? The silver nitrate solution is taken in both the cells, and two silver electrodes we have dipped into the solutions. So what happens, the silver nitrate of one of the cell, if we go on titrating with the KCl solution very slowly with small aliquot of KCl, and with every addition of aliquot we measure the EMF very at small intervals, say 0.5 ml or 1 ml, and at the point where the drastic change in EMF is obtained, we get the equivalence point of the precipitation titration, wherein the complete silver chloride is precipitated out. Now, in order to make sure that the complete chloride ions are utilized, or silver ions are utilized, we can calculate the concentration of chloride ions. And once I know what is the concentration of my chloride ions, so I know the concentration of silver ions, so I can find out the solubility product at equivalence point. In the same fashion, the concentration of chloride ions can be calculated at two more stages, just to make sure that whether the complete precipitation has been taken. So even after equivalence point, I can take the two concentrations of chlorides, and at these particular two concentration, I can find out the solubility product, and I can make sure that my solubility product is correct or not. At even after the end point or neutralization point, or after the complete precipitation of silver chloride, even I can find out the chloride concentration, and at this particular concentration I can find out the solubility product, so as to make sure whether complete precipitation has been taken place, and I can determine the solubility product at two more concentrations even after the equivalence point. So these are all are the applications of EMF. There are other applications as well. We will see all of them in our next part of this particular lecture. So friends, we will stop here in this lecture, and we will see the remaining part of this lecture in our next part. Thank you.